Recording now. Okay. Welcome everybody. Good morning, good evening, good afternoon, depending on wherever you are in the world. Today it's my pleasure to have here Clara Grazian as next speaker at our One Word ABC seminar series. Clara is a lecturer at the University of New South Wales in Sydney, and she will be talking about PET ABC, so fully Bayesian likelihood-free inference for kinetic models. The stage is yours, Clara.
Thank you, Massimiliano, and thank you to the organizer of the seminars for inviting me. It's great to see so many people that I would like to see in person, but at least I can see online. So I'm going to present some work which is probably in terms of computational novelty is not much on the side of the algorithmic part, but it's more on the application. And it's some work I've been doing with some collaborators of mine from UNSW, Yannan Fan, and two collaborators from University of Sydney from the medical side, Stephen Michael and Gail Menus. So the work is based on images coming from nuclear imaging technologies, which is one of the main measures of non-invasive analysis of the body, in particular for physiological functions. The idea is that a subject is administered a radiopharmaceuticals, and then which emits some radiation. And so there is a machine detecting this radiation coming from the tracer. The main nuclear technologies are PET, positron emission tomography, SPECT, and all the data I'm going to present today or tonight is come from PET technologies. You can, like, this type of technology can be applied to many type of functions. They have been applied a lot on cancer detection and evaluation. They are applied on cardiac imaging or images for blood flow. And they represent one of the main type of analysis of the living brain, so of the processes of the living brain, such as reaction to a drug or some type of physiological functions. So as I said before, a subject, so images collected from these technologies are in the there is a process to have that. So a subject is administered with a small amount of a particular tracer, and radiation is detected because the tracer decay and produce photons. And photons are detected by a machine external to the subject. So usually what happens is that the machine represents a ring around the subject, and the energy of the photons must be high enough to allow the photon to leave the subject, but low enough to allow absorption by the detector. So what happens is that we have a PET camera, which is organized in 24 block detectors, and each of these block has two photomultiplier tubes, which are attached at a crystal with amplify the signal and allow localization of the interaction. So what you obtain from PET imaging is some images, of course. So the goal of the imaging is to study the concentration of radioactive nuclei coming from the object from which we are taking the image. Of course, the image is in terms of is a 3D image. So you get a volume, and the volume is subdivided into non-overlapping volume elements called voxels. And you can observe the radiation for each voxel. Then you have a 3D image, but it can be followed over time to get a dynamic imaging, where changes of the traces are investigated. And usually you observe the image in changes of 30 to 60 minutes, and the time frame is divided into frames like between 20 and 60 usually. So what you get is this type of images recorded over time. And what you would like to study usually is these so-called time activity curves, which represent the activity of the tracer over time. And I'm going to talk a bit more about that later. So as I said, the images come in 3 dimensions, and you get slices of these 3-dimensional images. And then what you would like to do is trying to, so you may apply a model of the activity you would like to observe, and you may estimate, you may want to estimate the parameters of this model, so that then you can reconstruct the image by coloring the areas of interest depending on the parameters you have estimated. So you would like to obtain some meaningful information from the time activity curves that can be translated into a particular type of activity in the brain or the organ of interest. So what is usually, so this type of analysis is usually called functional analysis or functional imaging. And it studies how the tracer accumulates and clears from the tissue. And in this way, it is possible to associate this type of activity of the tracer to some physiological function. The parameters of the models can be estimated for each voxel separately, so for each of these images, or for groups of images representing a particular ROI, sorry, which is region of interest, or even for all an organ, or even for all the body. And I'm going to present some results for each of this type of problem. As I said, so usually this type of researchers assume some type of models, and I'm going to present them in a moment. The golden standard in terms of inference for kinetic models is least square estimation. And there are different types of least squares, like nonlinear, non-negative, weighted, depending a bit on the type of model. And with least squares, the aim is to fit and to fit the model so that you can represent the time activity curve. The problem with the least squares is that they don't provide much information on the reliability of those estimates. And in some cases may tend to overfit and to follow too much the data. But as I will show in a moment, the quality of the time activity curves, the information coming from the time activity curves may be very variable depending on the quality of the image. And so there could be a lot of noise, and it is good to have a procedure which is robust enough to allow for those levels of noise. Bayesian methods are also like there are some proposals for applying Bayesian methods to this type of problem. But in practice, what can be observed is that MCMC tend to be very slow in convergence and show a poor mixing. So this is one of the main reasons why Bayesian methods are not popular for this type of models, at least to the best of my knowledge. As I said, the most famous or popular models in this area are kinetic models, which provide estimates for some parameters which has a biological meaning. Usually, like some of the most popular kinetic models are the 1, 2, or 3 tissue compartment model, where one normally assumes that makes some assumptions on the tissues and on the state of the tissues. So for example, a classical assumption is that all the tissues see the same input function. And I'm going to present more graphically what an input function is. And this input function represents the measured concentration of the radioactivity in the blood. And then it is normally assumed that the system is in a steady state. The signal is uniformly mixed within each voxel. And there are like one or more chemical states. So in terms of what happens, we are in a situation like which can be represented by this graph, where there are so there is a particular tracer compound which is FDG, and I'm going to make an example of a data set with this at the end of the presentation. So the compound is delivered into the blood and transported into the cells. The compound can be seen in 3 possible states. One is within the plasma. One is present in the cells and between cells in the interstitial space. And one is seen only in the cells. Compartmental models are then built to describe the connection between the states and describing the fluxes to and the effluxes from each compartment in terms like in form of differential equations. So the 1 tissue compartment model is the simplest model that frequently is used in PET applications and describes the bidirectional flux of tracer between blood and tissue. So we have the concentration. So the target concentration is the concentration in the tissue of interest. And then there is the concentration seen in blood or blood plasma. And this represents the input function. And then there are 2 first order kinetic rate constants, K1 and K2. K2 represents the flux from the tissue to the blood, and K1 usually represents a diffusion from the blood to the tissue. And each, so it's like each state assign a compartment and the change of concentration are described by a differential equation. So the 1 tissue, sorry. So for the 1 tissue compartmental model, this is the ordinary differential equation. So there is a flux from blood to tissue, and this is described by K1CA. And then there is a flux from the tissue to the blood, which is described by K2 times CT. So the next tracer flux is indicated by this differential equation, which is solvable in an easy way. So just to summarize, CT is the measured radioactivity concentration in the voxel of the region of interest. CA is the concentration in the blood, which represents sort of reference. And then K1 and K2 represent the parameter of this model. More complex compartmental model distinguish different states of the tracer in tissue and may consider several tissues as well. Usually what happens is that, of course, so for example, the two tissue compartment model is a more complicated model where you assume to observe concentrations in two different tissues and having a reference or input function CP. And then there are fluxes from the blood to the first tissue, from the first tissue to the second tissue. Of course, you can assume more complicated models. But what happens is that the number of parameters will increase. And usually what the researchers do is to consider the two tissue compartmental model as a proxy for more complicated models. In the sense that the main concentration of interest is C1. And then fluxes from C1 to other tissues, which may be not just one, but several, maybe just organized together as one super tissue. So it is possible to use ABC in this context, and it's quite immediate because it is possible to relate the parameters directly to some quantities with a biological meaning. So the algorithm we propose is quite a standard rejection ABC with simulation of the parameters from appropriate priors, which we took uniform in some ranges provided by the experts. And from those parameters, a time activity curve is estimated, is simulated. And then the simulated time activity curve is compared with the observed time activity curve. And in particular, instead of considering time activity curves directly, we consider a smoothed version of them. And then we accept it or reject like in a classic ABC step. We did, so we mainly try to understood the practical and applied advantages of this type of algorithm in this setting. So we ran first a simulation study. We try to be realistic in terms of this type of experiment, and we simulated values from one tissue compartmental model. We used two types of noise. We added two types of noise to the time activity curve, which are usually used as assumption on the type of noise for time activity curves. One is Gaussian and the other one Poisson. We simulated data at 3 different levels of noise. So this is the type of simulation we did. So in one case, we had simulations quite close to the time activity curve, while then we increased the level of noise, which is possible to observe if the quality of the image is quite low. So the differences between simulated and observed data increase with the increasing noise level. So the choice of the tolerance level in the ABC algorithm was defined in a trial and error perspective. So it was decreased. So the tolerance level was decreased until the posterior distributions for the parameters were stable for several values of the tolerance level, until the value of the tolerance level was so small that the approximation was too poor to be considered a good approximation. And what we obtain is that so these are posterior distributions of K1 and K2. I hope you see my cursor. So the top row is for K1 and the bottom row is for K2. And these are for different levels of tolerance, different level of noise. So in particular, K1 is quite well estimated around the truth. So the vertical lines are dashed and dotted for the posterior means, and the solid lines are the truth. In terms of parameters, K1 seems to be better estimated than K2. While with because if we look at K2, when the level of noise increases, then the posterior approximation seems to be a bit bimodal. And a similar type of consideration can be done for Poisson noise. So K1 seems to be better estimated than K2, in particular for a higher level of noise. But very similar consideration depends on, can be seen with different true values of K1 and K2. More or less what we've seen is that the type of approximation can be good even in presence of larger level of noise. We also compared the ABC procedure with least squares, which as I said are the golden standard in this type of models. And what we observe is that the estimates tend to be quite similar, and as well as the variability. But again, the variability of the least squares tend to be a bit higher, in particular in presence of larger noises. One advantage of the ABC procedure is that it is possible to perform automatically, like in a natural way, model choice. So a classic example is, so in many situations, it is researchers prefer to use two tissue compartment models because they are more general. But it is better to use one tissue compartment model if they are a better assumption, because they are more easily to be estimated. So what we did was to like in this slide, what I'm trying to show is that naturally it is possible to estimate the time activity curve in presence of noise, but then also to perform a model choice by looking at the posterior probabilities of the two models. So in this first row, we have simulations from one tissue compartment model. In the bottom row, we have a simulation from the two tissue compartment model. And in the middle row, we have a simulation from a mixture between a mixture of the two models with 30% weight given to the one tissue model. So this, the second column represents the model probabilities for the one tissue compartment model for a greater values for the tolerance levels. And the last column represents the root mean square error for the parameter estimates, taking the truth as the best possible choice. The vertical line represents the point where the root mean square error is minimum for both models. And the vertical line in the second column is the same as the third column. So it is possible to see that in terms of the tolerance, so when choosing the tolerance level relative to the lowest mean square error, in the first case, we would choose model 1, so the one tissue compartment model, with a posterior probability around 0.60. In the third case, we would choose the two tissue compartment model because the one tissue had a posterior probability around 0.25. And interestingly, in the mixture case, the posterior probability of the one tissue compartment model is around 0.30, which is the weight from which we have simulated the data. So the weight of the one tissue compartment model from the model we've simulated the data from. So it's interesting to see that with respect to these squares, we have also sort of an automatic way to perform model selection as well. So so far, it was a bit of an introduction, but I would like to focus a bit more on the applications at hand. And in particular, what we had was a data set where data were acquired for a rat. And there were two PET scans were performed on the same animal on 2 consecutive days. One with some administration of like saline vehicle, and the other one with administration of amphetamine. And so we would like to see if this model, like ABC, would perform well in this situation with, so we would like to see that there is actually a drug administered in the second case, and we would like to see like no drug under the first day. So what happens here is that the one tissue and two tissue compartment models are not suitable for this particular problem, but actually what is more interesting to see is to see if the drug had an activation in the brain of the rat or not. So in the first case, we would like to see no activation. In the second case, we would like to see activation. So instead of using a one tissue compartment model, it is possible to use the LP and TPAT model, which has this form. So again, we study the concentration of the tracer in the target tissue given by CT, and the CR is the concentration of the tracer in the reference region, which represents a similar thing as the input in the one tissue compartment model. And then there are two parameters, like 3 parameters, R1, K2, and K2A, describing the kinetics of tracer in the tissue. And then there is a function H describing the non-static state component of the kinetic model. And the magnitude of this component is given by this parameter gamma. So you can see that if gamma is equal to 0, this last part of the formula is equal to 0. And so this is the case where there is no activation in the time activity curve, while with a positive gamma, you would observe an activation of the drug. And H is defined in this way. where there are two parameters, TD and TP, representing TD, the delay time at which the response starts, and TP is the peak time of the maximal response. And alpha is a parameter of sharpness of the response. So what we observe is that, so we have the two data sets, and we have vehicle and amphetamine with the corresponding 95% credible intervals represented by the shaded regions. What happens is that when, so in some areas, so in some voxels, we can actually, so in some data sets, we can actually see that gamma is equal to 0 in both cases. But when we observe gamma larger than 0 for the vehicle, it is usually associated with a posterior distribution for gamma very concentrated around 0, suggesting that it may not be different from 0 statistically. And under amphetamine, we observe that the posterior distribution when gamma is positive is actually concentrated around a value which is larger. And in particular, in this case, it's around 0.07. So this is for one voxel. So what we observe in one voxel, and we have one activity curve, time activity curve. However, what happens is that usually we observe many more images and many more voxels. Sometimes we may observe millions of voxels, and we would like to reconstruct full images. And so trying to perform an analysis where the parameters we estimate can be associated with a particular physiological function. So PET-ABC can be extended for a voxel-wise analysis. And the main point of this is that like ABC is extremely parallelizable. So we actually perform an analysis again on a mouse where there were 4 regions of interest in the brain. One was the striatum, which was the target region, one the cerebellum, which was the reference region, and then it was the rest of the brain and the head. The goal was to study dopamine activation, and like images like the PET data set was a dynamic PET data set, so observed over time in a 60-minute scan. More or less, there were 7,500 time activity curves and voxels, and they were corresponding to all the brain, and they were processed with the ABC algorithm I'm going to present in a moment. So in this case, we investigated 2 models, LP and TPET, which was the one I presented before, and the MRTM, the multilinear referent tissue model, which is the LP and TPET with gamma equal to 0. So we wanted to understand if there was activation of dopamine in the brain and in which area of the brain of the rat under analysis. So this is the type of activity curves that we can observe. So in the cerebellum, there is no activation. So we assume to observe this type of activity curve. The red line is an average activity over around 500 voxels in the striatum. So you can see that there is a difference. But the fact is that these 2, the purple and the green one, are 2 examples of voxels in the striatum. And there is a large noise and there is a lot of difference between voxels in the striatum. So where we assume to observe activation, actually what we observe is a large variability of the time activity curves. So PET-ABC works in a similar way as before, but in this step, we also simulated the model and we perform model selection, increasing the problem of the algorithm. So we simulate the model, and given the model, we simulate the parameters. Then we simulate the time activity curve depending on those parameters, and we compare that with the observed time activity curve, a smoothed version of the observed time activity curve. Even if it seems that it may be extremely time consuming, actually what happens is that the simulations part can be done offline and altogether. And then the voxel part, so the analysis per voxel can be done in parallel at the same time. And so actually the analysis of this high dimensional data set can be run in a reasonable amount of time. And what we obtain is posterior posterior distributions for an approximation of the posterior distributions of all the parameters, and including, more interestingly, parametric maps of gamma posterior distribution to see where the activation was in the brain of the rat. Again, it is possible to observe false positive or false negatives, but what happens is that when we observe activation in the cerebellum, that is where we're supposed to not observe, it is assumed that we can't observe activation of the drug. We obtain that when there is no time activation, the posterior distribution is quite concentrated around 0. It's not a good representation because actually we can also, this is the representation when we simulated and accepted model with activation, because we could make inference on the posterior probabilities of the models as well. But also when we accept the model with activation, the posterior distribution for gamma is not very different from the prior. So it seems that there is not enough information to inform the posterior distribution of gamma. While in the other cases, so in the brain and in the striatum, we actually observe posterior distribution for gamma in case of acceptance of the model with activation or with no activation, which are different. In some cases, even more different. So this is the type of reconstruction that I was talking about. So this is different views of the brain, and in particular, the brain is the light gray area, and the head is the dark gray area. And we can represent the level of gamma in terms of posterior means or intervals or any type of quantity of interest of the posterior distribution in red. And so you can see that most of the activation is actually in the striatum as expected, and sometimes in the brain. So which is this is a type of example where we would like to say we know what we would like to see, and we actually can see that we observe what we expected. But a bit more interesting is the last example I'm going to talk about today, which is a full body, like a total body scan. And the goal is analyzing like cancer detection. So a neurotransmitter tracer was a radio tracer was administered to the patient. So this is FDG, so it's not a neurotransmitter. So LPNT PET is not an appropriate model for this type of tracer. But in this case, it's more appropriate to use a 1 and 2 tissue compartment model. This is a total body analysis. So we have around 1.7 million images to analyze. And The model of interest for the researchers was a comparison between a two tissue compartment model, as I presented at the beginning, this one, or a two tissue compartment model where K4 was equal to 0. So we assume that there could be a flux from tissue 1 to tissue 2, but not from tissue 2 to tissue 1. And this is a representation that is more informative in this case in terms of cancer detection. So we performed, we used PET ABC to perform an analysis similar to this for all the voxels. And what we actually found was that we were able to represent the choice of the model together with the estimation of K4 was informative on the area where cancer was, and also on the different tissues within the same cancer. So for example, these are all types of cancer. And in other areas of the body, we identified again cancer here and here. So just to give a conclusion, ABC, like even this standard version of ABC, is easy to interpret, but also easy to perform algorithm for kinetic models. And with respect to standard least square methods, it allows for a natural incorporation of the uncertainty. And what we have observed in practice is that the estimates tend to, the estimated time activity curves with ABC tends to overfit the data less than the squares. The main advantage of ABC in this setting is that it is easily parallelizable. And so a lot of images can be analyzed at the same time. Of course, there are some limitation of the algorithm so far that we are investigating right now. In particular, as I said, the version of ABC we are using is quite standard and easy. Smoothed version of the time activity curves seems to be a good choice of the summary statistics, but maybe there are better choices, and I'm happy to get any comment. And an interesting fact that we are considering right now is how to introduce spatial information in the voxels, because of course you may think, so it is reasonable to assume that there is some similarity in the, so like voxels, like voxels in proximity tends to be more similar than voxels which are far apart. So it would be interesting to introduce this type of spatial information in the model as well. And just to conclude, we have developed an R package to make this analysis. For the moment, the one available is based on the voxel, so the specific voxel analysis. But we are also preparing the one for the voxel-wise analysis. And there is a bit of bibliography. So thank you very much for coming today and for listening. And I'm happy to get any question you may have.